Hi, in the last video, we looked at how the differential gain was equal to the half circuit gain. We proved that in the video before that using the large signal model, and the very last video, we also proved that intuitively. We are going to prove that another way, which will lead us to what we call the half circuit gain, which can be very useful when solving gains of differential amplifiers. So before then, we just start by drawing a differential amplifier once again. Then we connect the tails to a current source. For now, we are assuming the current sources are all ideal. Alright. Okay, so we've already proven that for small signal changes, if there's a small change in V in 1, then there will be a corresponding small change in VBE in 1. Okay, and if it's a differential signal, meaning the VB in 2 will change in the opposite direction, then the VB in VBE2 will also change in the same direction opposite to this one, which basically means the voltage at this node, call it node P or node T, will remain constant. We also know when doing small signal analysis, all voltages that do not change with respect to time are usually grounded. So I can really draw this as a small signal equivalent this way. Okay, so the current source is also replaced by an open circuit for small signal analysis, because it's also not changing with respect to time. Then my equivalent circuit is going to look like this. This being node T, this also being node T. So I can draw the single differential circuit as two half circuits. Okay, now let's see the small signal gain of this common emitter stage circuit. With a change in V in 1, the gain, as we already know, is expected to be so the output will be the change in input, which is V in 1, times the gain, which is going to be GM-RC. So negative. Similarly, a change in V in 2, let's say the small change voltage applied is V in 2, then the output is expected to be V in negative V in 2 with the transconductance GM-RC, where this is RC and this is also RC. So we are used to this from the single stage common emitter amplifier. Okay, so what we want to do now is to find the differential gain. So the differential gain is going to be the differential output V out 2 minus V out 1 all over the differential input, which is V in 2 minus V in 1. Okay, so we have our differential output here minus V in to GM RC minus this, which is V in, we're going to be minus V in 1 GM RC all over the differential input V in 2 minus V in 1. Okay, so I'll give myself some room here. Okay, so if I do factorize out V in 2 minus V in 1, then I'm going to get something like minus GMC factorized out so what is left here is going to be V in 2. One of the minus has been factorized out here, so I'm left with minus V in 1 all over what we had before, V in 2 minus V in 1. Okay, so this cancels that. Then we confirm that this differential gain is given by the half circuit gain. And this is useful in working out gain of a differential amplifier. You can also be given the cascade. So just as we have cascade amplifiers, we can also have a cascade differential amplifier, which will look like this. Okay, before we look at the cascade differential amplifier, we can try and find the gain of this circuit here. Alright, so assuming I have something like this, so this is an example. Find the gain of the circuit. Okay, so I should have said find the differential gain of the differential amplifier, which is still the circuit. I'm going to draw a differential amplifier this way with a VCC. So this is RC, and this time I have emitter degeneration here. So emitter degeneration could also be applied to the differential amplifier, and all the advantages we get from emitter degeneration in the common emitter stage also applies with the differential amplifier, which you are going to see pretty much soon. Okay, and our tail current source. Okay, so we are asked to find a gain, and from our prior knowledge we know that the differential gain we've proved this 3 different times and they all give us the same thing. It's called the half circuit gain. So what we are going to do is find the half circuit and produce or easily calculate the gain of the half circuit, which should be equal to the differential gain. So let's redraw the half circuit, and we know it's going to be RC then our bipolar device comes. So this will be our input. Then we have RE, the emitter degeneration resistor. And this node is grounded or has an AC ground, so small signal changes. And this is an open circuit. So I just end with a ground. So the gain of this half circuit should be equal to the gain of the differential circuit here. And from our basic electronics, we should know the gain of a common emitter stage with degeneration. So you know that that is just equal to whatever is tied between the collector and the ground. In this case, you have only RC. We are just neglecting the effect here, together with 1 over GM of the device plus RE. So assuming there's no RE is equal to 0, all this is equal to 0, this term moves back up, then you have our negative, so there should be negative here, our negative RC GM, as we already know. Okay, so this becomes the gain of the half circuit, which is also equal to the gain of the differential circuit. So in the next video, we'll look at much more complex circuits. What happens if we want to find the gain of a cascoded differential amplifier? Until then, see you. Bye.